Hey everyone, in this video we are going to learn how to multiply, divide, and rationalize square root expressions. Before continuing into this video, make sure you're confident in simplifying square root expressions, as we are going to need to do that as well. So in order to multiply radicals, we first multiply the coefficients, then multiply the radicands. Put differently, we're going to multiply the numbers in front of the radicals together, then separately multiply the numbers inside of the radicals together. That product of the radicands, the numbers inside, is placed under a single radical, and the last step is to check if the radicand can be simplified further. So let's look at two examples to see how this works. So our first example, 4 squared of 2 times 3 squared of 7. So the coefficients are 4 and 3. We multiply them together to get 12. Then square root of 2 times 7, which is the product of the radicands, that would give us 14. And then we have to check if we can simplify this further. So 14 does not have any perfect square factors, so 12 squared of 14 is considered simplest radical form, and that would be our answer. Moving to our next example, we have 5 squared of 6 times 2 squared of 3. Multiply the coefficients, so 5 times 2 is 10. Then square root of 6 times 3, the product of the radicands, which is 18. Now 18 does have a perfect square factor. It is 9, and that would be the largest perfect square factor. Remember, our goal is to factor with the largest perfect square. So we have 10 times the square root of 9 square root of 2. So 10 times 3 square root of 2, which is 30 square root of 2. And that would be our answer in simplest radical form. So we start by getting the product of 10 squared of 18. Then we go through the process of simplifying to get the answer of 30 squared of 2. So that's what multiplication looks like. Now for division, in order to divide radicals, we first divide the coefficients, then divide the radicands. So very similar. The quotient of the radicands is placed under a single radical. And the last step is to check if the radicand can be simplified further and that the expression is in its simplest form. So here we have to check for two simplifications. Can the square root be simplified? And then can the larger expression be simplified further? So let's look at a few examples of division. So our first example is 3 squared of 14 divided by 15 squared of 7. So we divide the coefficients. So 3 divided by 15 reduces to 1 over 5. Then we divide the radicands, so 14 divided by 7 is 2, so that gives us a square root of 2 in the numerator. And we can rewrite this as square root of 2 over 5. And that answer is in simplest radical form, since 2 cannot be factored any further with perfect squares. Next, we have 12 square root of 8 divided by 4 square root of 2. So we divide the coefficients, so 12 divided by 4 is 3. Square root of, divide the radicands, so 8 divided by 2 is 4. So we have 3 times 2, which is equal to 6. So this is an interesting result because we do not have a square root in our answer here. And that can happen sometimes when we're multiplying or dividing square root expressions, that we wind up with an answer that no longer has a square root. Then we have 9 square root of 260 divided by 36 over square root of 13. So divide the coefficients, so 9 over 36 would give us 1 over 4. Then divide the radicands, so 260 divided by 13 is 20, so square root of 20. Now square root of 20 can be simplified further, so we're going to rewrite that as square root of 4 times the square root of 5 over 4, which is 2 square root of 5 over 4. So now we simplified the square root expression, but now we can also simplify the expression we have for our answer. The 2 and the 4, the 2 in the numerator, the 4 in the denominator, those can divide or reduce. So this is equal to square root of 5 over 2 in simplest radical form. So when we refer to simplest radical form, it means not only the most simplified square root expression, but also the expression as a whole needs to be in its simplest form. So let's look at a few more examples of multiplying and dividing. So the first one, written a bit differently. So we have 3 squared of 10 squared. So remember, exponents are repeated multiplication. So this is really 3 squared of 10 times 3 squared of 10. So we go through the process of multiplying. So 3 times 3 is 9. 10 times 10 gives us a square root of 100. So this is going to be 9 times 10, since 100 is a perfect square. And remember, we don't rewrite a square root symbol if we take the square root of a perfect square. And 9 times 10 is 90. Again, we started with square root expressions. We took their product, and we wound up with an answer that no longer had a square root here. Our next example, 7 square root of 8 times square root of 6. So make sure we understand that there's a coefficient of 1 there, even though no number appears. So the product of the coefficients, 7 times 1 is 7. Product of the radicands gives us square root of 48. And now 48 does have perfect square factors, the largest being 16. So 7 square root of 16 square root of 3. 7 times 4 square root of 3, which is 28 square root of 3. And remember the process we talked about in the previous video. If we're not sure, we start by taking half of the radicand, so that would be 24 and 2. 24 is not a perfect square, but it gives you a starting point, and you can work down from 24, checking all your perfect squares. Right, so after 24, you would try 16, 16 then try 9, 9 then try 4. In this case, 16 worked as a perfect square factor. But just to reiterate the process to help find the largest perfect square factor. Now to division problems. So we have 9 square root of 150 over 27 square root of 3. So the 9 and the 27 we can divide. That gets us 1/3. Then 150 divided by 3, that's going to be square root of 50. Now the 50 can simplify, so that's square root of 25 times the square root of 2 over 3, which gives us 5 square root of 2 over 3. And that's our answer in simplest radical form. Now we have 24 square root of 605 over 3 square root of 5. So 24 divided by 3 gives us 8. And then 605 divided by 5 is 121. 121 is a perfect square, so we have 8 times 11, which is 88. And again, we see an example where we were dividing two square root expressions and got an expression without a square root as our simplest answer. Now, what happens when the larger radicand is in the denominator? All the examples that we've looked at so far, the larger radicand has been in the numerator, and that works pretty nicely for us. So if we look at our first example, 16 square root of 8 over 12 square root of 32. So we go through the same process, divide the coefficients. So the 16 over 12 would reduce to 4 over 3. Then we divide the radicands, but in this case it's more like reducing since it's 8 over 32. That will reduce to 1 over 4. So we're going to write the square root of 4 in the denominator. Right? So if it was square root of 32 over square root of 8, it would be square root of 4 in the numerator. But now, the larger radicand being in the denominator, we place the square root of 4 in the denominator. So then this gives us 4 over 3 times 2, which is 4 over 6, which simplifies to be 2/3. Our next example, 21 square root of 10 over 14 square root of 20. So we divide the coefficients, so 21 divided by 14 is 3 over 2. And then 10 over 20 would reduce to 1 over 2. So we have square root of 2 in the denominator. Technically, just to address this, technically there would be a square root of 1 in the numerator, but that's 1, so we can skip over that step. But for technical purposes, it would be there. And now we have a square root in the denominator, which is a problem. If you recall from the previous video, there were 3 rules for something to be in simplest radical form. The radicand could not have any perfect square factors. there could not be a fraction inside of the square root, and there could not be any square roots in the denominator, which we have here. And that leads us into our last piece of rationalizing. So, how do we deal with an expression that has a radical in the denominator? It's through the process of rationalizing the denominator. So let's start out with a goal. We want our goal to be a denominator that no longer has a square root in it. So we need to multiply the square root of 5 by another value that is going to give us a number that is not a square root. So one choice we have is the square root of 5, because the product here is going to be the square root of 25. 25 is a perfect square, and that would give us 5 in the denominator. So by multiplying by the square root of 5, we were able to create a perfect square radicand, which then simplifies, so we no longer have a square root or a radical in the denominator. But we cannot just arbitrarily multiply by whatever we want, right? We can't take a poor test grade and multiply by 2, so all of a sudden it seems like a better score. But what we can do is multiply by 1, and that's based off the multiplicative identity property. So we want this value, so we want this to be 1. Well, when we're working with a fraction and we want it to be equivalent to 1, that means the numerator and the denominator have to be the same value. So if we chose square root of 5 in the denominator, then we have to choose square root of 5 in the numerator. That would reduce to 1 if we were to reduce it. So 1 times square root of 5 gives us square root of 5, and we get square root of 5 over 5 as the answer in simplest radical form. So really this is a clever multiplication approach where we are multiplying by 1, but writing it in a way that accomplishes our goal of no longer having a square root in the denominator. And this process is called rationalizing the denominator. Now, just to address, it didn't have to be square root of 5. We could have chose square root of 20, for instance. 5 times 20 is 100. 100 is a perfect square. Square root of 100 is 10. And we would still get our same outcome. The only thing, if we choose larger values, we may have to simplify more. So we would have to simplify the square root of 20 in the example that I'm speaking through. And it just adds an extra step. Not more difficult, just an extra step. So let's formalize this. In order to simplify the expression, we must rationalize the denominator. Now, why do we do it? We do it when we're adding, subtracting, comparing fractions, right? For instance, if we were trying to do square root of 2 plus 4 over square root of 2, right? The way that it's written, those are not like terms. But if we were to rationalize, so I'll do that quickly here as another example. So 4 over square root of 2, we can multiply square root of 2 over square root of 2. So that would give us 4 square root of 2 over square root of 4. 4 square root of 2 over 2, which is 2 square root of 2. So then this original addition problem that I wrote really is square root of 2 plus 2 square root of 2, which is 3 square root of 2. And we see that they were actually like terms, but we would not have known that if we were not able to rationalize the denominator. Right, so just giving some motivation other than this random process that you're being taught. Okay, so let's go through a couple of rationalizing to practice. So we have 6 over square root of 3. So we're going to multiply by the square root of 3 over the square root of 3. In the denominator, that's going to create the square root of 9, which is 3, which is our goal. In the numerator, we'd have 6 square root of 3. So we'll rewrite that again. And now simplest radical form, we can simplify this expression one step further. the 6 and the 3 divide to give us 2 square root of 3. Next, we have an example with a coefficient here. So we're not going to include the coefficient in our work. We're going to still focus on the square root of 2. So we're going to multiply by the square root of 2 over the square root of 2. So we get 3 square root of 2 in the numerator. And then 3 square let's write that correctly, 2 square root of 4 in the denominator. So we have 3 square root of 2 over 2 times 2, 3 square root of 2 over 4. Next, we have the square root of a fraction. So as we looked at in the previous video, the first thing we want to do is rewrite this as square root of 2 over square root of 7. Now we have to go through the process of rationalizing the denominator. So we can multiply by the square root of 7 in the numerator and the denominator. So that's going to give us square root of 14 in the numerator. We multiply the radicands and that product stays under the radical, over the square root of 49, which gives us square root of 14 over 7. Okay, I'm actually going to add one last example here. So let's make it, let's say, 3 over square root of 18. Okay, let's say we want to rationalize 3 over square root of 18. Your first option could be to multiply by the square root of 18, square root of 18, right? Multiplying anything by itself will always create a perfect square, and it's a great strategy to have. But there are examples, this being one of them, where if we can choose a lower number, we're going to have less work in the simplifying process. So I'm going to erase this. So another option could be to multiply by the square root of 2 in the numerator and the denominator, because the product of 18 and 2 is 36, which does create a perfect square. And it's a smaller perfect square value, so we may have less simplification to do. So if this is something you notice, I would definitely encourage you to use this strategy when we're rationalizing, and don't always fall into the habit of just multiplying a number by itself. That always works, but there could be a better way to do it. So then here we have 3 square root of 2 over square root of 36, which is equal to 3 square root of 2 over 6, which simplifies to be square root of 2, not 3, square root of 2 over 2. So we have practiced multiplying, dividing, and rationalizing. Especially the rationalizing is new, so it's going to take a bit of extra practice. But go through all of this, practice your simplifying square roots, and hopefully you feel confident now having practiced and gone over all of these operations.